Here's an example of free damped vibration with some values for m, b, and k, as well as some initial conditions. So notice that the initial position is at -1/2 and the initial velocity is -1. So depending on which way you measure your y, this thing is away from the equilibrium by 1/2. So let's say it's above the equilibrium by 1/2 if we're measuring y downward, and then the initial velocity is away from the equilibrium. So it's about a half unit away, or exactly a half unit away at the beginning, and then it is initially moving away from the equilibrium. So when we look for the maximum displacement, we expect it to be more than a half away from the equilibrium at some point, but then um, it'll oscillate, and we'll see what kind of oscillation we have, whether it's underdamped or overdamped or critically damped. So we gotta start solving this with these values. Our equation looks like this. Remember, my double prime plus by prime, since b is 1, just y prime, and then ky. Again, this is free vibration, so it equals 0. And then solving this, we set up the characteristic equation. So we have 1/4 r squared plus r plus 4. And then to solve this, use the quadratic formula. So you have -1 plus or minus the square root of 1 squared minus 4 times 1/4 times 4. So it's just 4 in the end, all over 2a, 2 times 1/4, so divided by 1/2. So simplifying a little bit, I'll save you the time to simplify. You should get -2 plus or minus 2 root 3 times I. Notice that b squared minus 4mk is negative, and so this is the underdamped situation where we have complex solutions for r. So our general solution y is going to be c1 e to the -2t sine of 2 root 3 t plus c2 e to the -2t cosine of 2 root 3 t. Given the initial conditions we have, we can solve for c1 and c2. The algebra gets a little bit tedious, but we can try it and find those. So using the first initial condition, that y of 0 equals -1/2, -1/2, plugging in t equals 0, we have c1 times e to the 0, which is 1, times sine of 0, which is 0, plus c2 times e to the 0, which again is 1, cosine of 0, which is also 1. So we get c2 equals -1/2. And then we have to take the derivative. Now the derivative for this, we have to use the product rule a couple times, so it gets a little bit long, but briefly what you should get will look something like this. So that's the first part from the product rule on this first term, and then the other half of that would be 2 root 3 c1, etc., with the cosine. And then we do the same thing to the second half using the product rule again. So we have -2 c2 e to the -2t with the cosine, minus 2 root 3 with the sine function. And again, if you want to go back and verify that using the product rule, feel free, but it's just more tedious than anything. It's not actually difficult to do that derivative. And then we can plug in the second initial condition, that y prime of 0 equals -1. So we have -1 equals, now starting to plug in zeros, this first term has a sign in it, so that'll go to 0. And this last term also has a sign in it. So those both go to 0. And all that's left is 2 root 3 times c1 times e to the 0 is 1, cosine of 0 is also 1, minus 2c2 e to the 0 is 1, cosine of 0 is also 1. So again, it's convenient to have initial conditions because a lot of those things simplify greatly. Since we also know what c2 is already, we can plug in -1/2 here, and we get -1 equals 2 root 3 c1 minus 1. sorry, plus 1. So we can subtract the 1 from both sides. We get negative 2 equals 2 root 3 c1. So c1 equals negative 1 over root 3. Which means our final solution looks like negative 1 over root 3 e to the negative 2t sine of 2 root 3t minus 1/2 e to the negative 2t cosine of 2 root 3t. So it's kind of complicated, but it's really just a combination of exponentials and sines in a familiar form that we've seen before. So there's our solution, and now we're looking for the maximum displacement. Now, what we can do is we can look at the graph of this. So if we graph this function, it will look something like this. Again, it's underdamped, so we expected to see the situation where there's some oscillation. Notice the initial condition here at negative 0.5. Let me move this graph into the notes real quick. So we have the initial condition at negative 0.5 or negative 0.5. And again, it starts out moving away from the equilibrium, so it starts out moving downward. And then we see this oscillation where it trends downwards. That's the underdamped situation. That's what we expected to see. Now, if we're looking for the maximum displacement, that's going to be right here. And so we're looking for where that maximum displacement occurs. Now, there's a couple ways to do this. If you could use a calculator to do this, we can take advantage of sort of built-in functions to find maxes and mins and things like that. Really quick, I'll just show you how you would do this in, say, a Calc 1 class where you're trying to maximize something like this or find the critical point. So we'll go through the Calc 1 problem. It's a little bit tedious to parse through, but let's try this. So if you've got y of t, now we already know the derivative. We already found that right here, where we found y prime. And now that we know the values of c1 and c2, we can just plug those in. So let me take that derivative and I'll sort of combine things together where these two terms have the same form, e to the negative 2t times the sine, and then these two also have the same form. So I'll combine those together. So in short, we get something like this. So the first gives us 2 over root 3 plus root 3. These are the sine terms. And then for the cosine terms, negative 2 plus 1. And so on. You can go back and check that if you like, but I'm not going to spend a lot of time going through it. So just to simplify a little more, we can pull out an e to the negative 2t, and we'll get something like this, where we'll have 5 over root 3 times the sine of 2 root 3t minus 1 times the cosine of 2 root 3t. So if we're looking for where this equals 0, again, we're trying to maximize or minimize y, trying to find the critical point, so we're looking for the derivative equals 0. Again, we've used this before, this exponential term is never going to equal 0. It has a horizontal asymptote at 0. So we're really solving where this equals 0. So really, this problem turns into trying to solve this question, where this minus the cosine is equal to 0, or this equals the cosine. And if we're trying to solve that, we can do this by dividing both sides, dividing both sides by the cosine. So we get the tangent on this side, and then multiplying by root 3 over 5 on both sides as well. So we're trying to find where this tangent equals root 3 over 5. At this point, we would really have to turn to a calculator because that's not a value that we know off the top of our heads probably. So it turns out that t is about 0.1 seconds. So about 0.1 seconds after the start of this experiment is when it reaches the max displacement. So if you want to know what that max displacement is, you would plug that into y, and it turns out that it's around 0.55. So the magnitude's around 0.55, just over a half. And of course it's negative, it's below because of where the initial condition was. So that's your max displacement. Now realistically, of course, you wouldn't do this by hand. You would use a calculator anyway, but I just want to take an opportunity to do a little Calc 1 problem with you and show you how to find this maximum displacement that way. So that's one way to solve this problem here, is to use what we know about homogeneous second-order equations to set up the characteristic equation and solve for the values of r, and then we know that the solution looks like this. Just for fun, I want to show you how you would solve this same problem using Laplace, but I think I'll make a separate video for that. So I'll show you the alternate solution using Laplace transforms, and that's where we'll wrap things up for this section.